I think we'll start now. It's 11:02, so as people will join, I mean, I'm going to start the introduction and start the webinar. So for everybody's information, the webinar will be recorded and will be available for all the participants to have a look after the presentation, after the webinar. We'll also be collecting questions as we go in the chat. These questions will be answered either during the presentation or at the end of the presentation. If there's too many questions, we'll answer after the webinar in the following days. So don't hesitate to send your questions that will be answered. So thank you all for joining us for this webinar on ground improvement for tailings dam. The presentation today will be given by myself, Hubert Guimont, and by David Schmid, my colleague, project manager for the mining division of Menard Canada. Our agenda today. So first, I'm going to say a few words about Menard Canada, who we are, where we're from, what type of techniques we offer. Then we're going to jump into one of the main topic of today's presentation, which is how to use ground improvement to improve dam stability. So we're going to cover the different aspects, the classical approach. And then we're going to look at two different techniques, the stone columns and the soil mixing. Then Dave is going to cover seepage control and construction sequence optimization. So we have roughly 45 to 50 minutes of presentation to cover all that. We have approximately 60 slides. So I'll get started right away. So Menard Canada. Who are we, and what type of problem do we solve? So Menard Canada has been a design-build ground improvement contractor for over 50 years now in Canada. Our name comes from Menard, Louis Menard, who's the founder of Menard, who invented also the Menard pressure meter in '55. So we're a long generation of geotechnical engineers trying to improve ground improvement and trying to bring new techniques through the years. So we've developed different techniques and different tooling in order to perform better and better work in ground improvement. Menard Canada has 7 different locations across the country, so we cover pretty much all the territory. We're not only doing mining, or we don't only do mining projects, but we also cover all sorts of projects in different industries. So it can go from very small project for a residential building to a mining project with large dam structure, multiple rigs, etc. We do have tons of different techniques, really, and combination of those techniques and all that. So we're really doing design build, in-house design build. And so today we're gonna have a look at 1 or 2 of those, maybe 3 or 4, let's say, of those techniques. But know that we also offer other type of techniques. Also, what could be good for you to know is that Menard is a worldwide company, right? We offer the same type of services all across the globe. So if you contact us here or in the next weeks for a project here in Canada, or for a project in Argentina, we can bring our team and our knowledge and our design skills to do the same quality type of work all around the world. So that could be interesting for mining clients and for a consultant that working on in different countries. So that's it for Menard's introduction. So now we'll go right into the first topic, which is the stability improvement. So this is not something new for probably most of you. Tailings dam have been concerned for many years now. There have been recent failures that brought those tailings facilities into broad light. Mount Poly in Canada is a good example of that. If we go back into the historical trend, this is from iCold, we can see that failures are mostly caused by ground instabilities, actually. It can be slope instability for static failure. It can be foundation issues, or it can be also related to seismic instability. So when you look at the different types of instability, you can see that the foundation and the stability concerns are one of the most critical mode of failure. I've put little signs here of where Menard can work on different solutions. So of course, we can work on static failure, earthquake, seismic instability, foundation, improving the foundation, but also on seepage and internal erosion, right? By building cutoff wall, for example. So the typical structures or the typical ways of doing stability upgrade. We'll go through a very large summary here, but the first option would be to let's say you have an existing structure and it doesn't meet the stability criteria, or you have lower safety factors. One of the most extreme solution would be to reconstruct, basically, so a total reconstruction. This, in most tailings facility, it's not possible. That would be only applicable, or mostly applicable, should I say, for water retention dams. Of course, here you're just excavating and rebuilding, so you just build from scratch, build new. Second option, that are the most typical one, I would say, are the major, which is major remediation. So working with the existing structure and getting it bigger and sturdier. So in that case, you can see here on the right what it means is basically building a buttress, a toe buttress, for example, and raising the crest of the dam. So you're trying to improve the stability by working with the geometry of the dam itself. So after that, if not enough, for example, if your safety coefficients are not high enough, the other step would be to try to work with the foundation improvement. One of the most typical way of doing that would be excavate and replace. Excavate and replace is usually good up to a certain depth. Of course, when you do excavation and replace, you have to manage first the stability of the dam itself, but you also have to manage the stability of the slope of your excavation, plus control the seepage while doing it. That can bring different problematic while doing that type of work. So that's typically limited to fairly shallow application. When you need to go deeper or bring extra stability, then we have different techniques that are mostly ground improvement techniques. So this is the topic of today. So the first category of ground improvement techniques will be applicable mostly for densifiable soils. So what does that mean? Densifiable means granular soil mostly. So for that type of soil, we can use techniques such as dynamic compaction, vibrocompaction, or blast densification even. So the idea is to really use the soil itself and try to improve its degree of compaction so it better perform, so you have a better stability. Sometimes though, and most of the times when we get involved in a project, that soil solution is not enough. So the next step in terms of robustness, I would say, is ground reinforcement. So ground reinforcement implies that we need to incorporate granular material or cementitious material into the soil mass and create a mass treatment at the toe berm foundation. These techniques are, for example, stone columns, deep soil mixing, jet grouting, or cement bentonite walls. Of course, there's a gradation in those techniques. If you incorporate stone columns, for example, you can be improving up to a certain level, meaning by that stone is less rigid than concrete, for example. So if you need more rigidity, you will, or more shear strength, you will switch for concrete. Then there's different patterns you can do as well. So you can do a mass treatment of stone column, or you can do also a grid pattern or shear panel. So there's multiple configuration that you can use in order to stabilize the toe berm, and that will depend on the type of soil that you have in place, and also the performance criteria that you have in terms of stability. Some applications are also better for some type of concerns, like stone columns, for example, could be used to mitigate liquefaction. Deep soil mixing as well, but then it implies different theories and different type of approaches. So worldwide, here's a little graph here showing the embankment height versus treatment depth for different type of structures. So it's mostly water retention dams and tailings dams that are plotted here. So on that graph, what we can see is that most of the lower, let's say, lower height embankment are typically best treated using stone columns. And as the depth, the treatment depth, and also the embankment height increase, designs are typically requiring more shear strength resistance and more shear strength, and it goes towards more like soil mixing application. So I'll continue and I'll start talking about stone column. So stone column to improve stability of the tailing dam. So just a little quick background on what is a stone column. So vibro replacement stone column is built by using a probe, a vibrating probe that is inserted into the ground, and we're building. So it's an electric motor that is vibrating and oscillating, and so it's vibrating the soil, but also enables you to build a stone column by either the wet top feed method. So basically, in there, you're just driving the probe down to your targeted depth, and as you go up, you pour some stone from the top, and you build a column from the bottom, making sure that you put the energy, the vibration energy, into the column, and so you're building a system of stone column doing that. The other method, which is the dry bottom feed method, is a bit different. You'll be injecting through the tube here, through the vibrating tube, in order to shoot the stone at the base of the column. So that's called the dry bottom feed method, and it enables you again to build that type of stone column. So two different ways of building the same final product. So I'll give you a very simple case story here that project that we've performed in Sudbury area. So the project has been using stone columns and wig drain, so vertical drain, to increase stability of a tailing dam. So there was a liquefaction issue. And plus, of course, we wanted to increase the stability factor for the existing dam. So the solution we came up with, working with the consultant on that job, was a combined solution, as I said, of stone column and wig drain too. Why did we design it that way? Is that we were scared, or we were not scared, but let's say concerned by the poor pressure that we could generate in the tailings while installing the stone columns. So what we've designed is basically first a pressure relief well system, so which is basically a very tightly installed stone column wall all along the toe of the tailing dam, in order to try to cut any excessive poor water pressure that could develop in the treatment zone. So we've installed a series of those wells, that interconnected stone column, basically, before performing the work here. So we've performed, and then we installed the stone columns, and then first we installed the wig drain, and then the stone columns, in order to stabilize the toe of that berm. So that's here you can see it in the cross section. So you can see that we were working in the tailings and going down to the native soil in order to treat for liquefaction. So the whole operation was really controlled and instrumented. So we did real-time monitoring during the installation. We did also a trial test in order to make sure that all the monitoring system and the pressure relief well was functioning well. That it's always a concern when you're working with a sensitive installation and you want to treat for liquefaction at the base of the dam, right? So we've started with a pilot test, a trial area right there, making sure that all the monitoring instruments were working fine and the procedure was giving or performing the way we were expecting. So you can see the wig drains here. You can see the vibro there. So really the idea was to try to dissipate as much as possible any excess water pressure that would be developing, and also helping with the densification process by just getting rid of the excess water while we were compacting the finer tailings. So here I'll show you just a very an overview of the post-trial results. So we've monitored everything. We did pre and post CPT, and this is a typical set of results. So you can see that we're improving everything that's coarser material, coarser tailings. Of course, when it's very slimy or very sandy material, silty material, the improvement is less. This is one of the characteristics of vibro replacement stone column, is that it still is a densification process. So the material needs to be densifiable for us to see an improvement. So that's the first example, showing, I believe, a good example of an upgrade, a stability upgrade. This one is for earthquake or seismic upgrade. And now I'm going to show you another type of example using deep soil mixing. So deep soil mixing is still a method of ground reinforcement. And there's many variation of that type of method. So there's many ways to install deep soil mixing. So it's important to notice that you know, you can do either wet soil mixing or dry soil mixing or high pressure, let's say, injection. So we've put here the jet grouting into soil mixing. It's partially soil mixing. Let's say it's almost soil replacement, and sometimes, but that could fall. Sometimes it could fall into the soil mixing type of application. So as you can see here on that graph, you have various types of soil mixing equipment and various type of configuration. Each type is more or less adapted to build different geometries or to different type of soils, and so it's important to select the good equipment. I'll show you a few different type of equipment that we can use. So the single axis soil mixing that's one example here, another here. You can see that the blades are different from soil type to other soil types. So that has an effect, of course, on production rate and also on mixing ability of the equipment. Sometimes you can have multiple axis soil mixing rigs. So that's most typically when you want to do linear geometries, right? So of course that type of equipment has limitation in terms of size of material it can mix. It's a bit more sensitive than, let's say, a single auger mixer like this one. So you have multiple augers like that example here. Otherwise, you have the CSM or cutter soil mixing. That's another example of mixing tool. Also mostly used for linear structures. That type of equipment was developed by our sister company, Soletange-Bachy, in the late 90s, I would say, working with Bauer. So this is the type of geometry we can build. Of course, here it's single axis elements that are represented. You can also think of panels, or you can think of multiple auger panels and different grids like that. So that configuration would be here mass mixing, 100% mass mixing. For severe cases, sometimes you need to do that. Most times, shear panels are used when it comes to stability. Shear panels are probably one of the most effective configuration, reliable configuration for improving stability. In some cases, where if you have an embankment height that's higher, or if you have liquefaction issues that cannot be treated with, let's say, conventional ground improvement techniques, the grid or box configuration is a very good type of configuration. Of course, when you do that type of configuration at the base or at the toe of a dam, you need to make sure that you're also thinking of the seepage through the structure, because that becomes a bit of an obstacle for the water flow. So that needs to be integrated with some hydrogeological concerns, of course. And here you have a discrete set of columns. This is a bit trickier because of course, when we do ground improvement, we want to do it's not a structural type of solution. It's a mass treatment type of solution. So here, when you're working with single elements like that, you need to be very careful when you're doing the design, so that it really is structurally validated, and that you're not exposing yourself to some structural failure of your single element. So for this type of application, so for deep soil mixing, I'll show you a project example that we've done recently in the Val d'Or area in northern Quebec for a site that was basically historically operating between 84 and 2013, and that was restarted in 2022. So they had to upgrade the facility and to make sure that everything was performing as requested by regulation. There was a requirement to raise the tailing dams to be able to accommodate new tailings. So all the geotechnical investigation were done, and many options were studied in order to do that. As you can see on the map here, many limitations. So on those sides here, northern and eastern sides, you can see the lake is very confining, and you have a certain distance from the shore that you need to keep. You cannot build your tailing facility straight on the shore. So there was environmental constraint here, and on this side, you can see that there's a railway as well. So pretty much very confined site, and the soil deposit was very soft and silty clay, so it needed really an upgrade, and there was limited time also to do the work. So many options were checked. The first option, of course, was the buttressing, just the toe buttress, trying to improve the stability just by adding material, as we discussed at the beginning of this presentation. Sometimes it was possible, but where all the stars here are plotted, there was not enough space, not enough room for the buttress to be built. So the size of buttress was too big. And in this zone here, well, the material was so soft that even a buttress would have not fixed the issue. So what was decided by the client was to go with a combination, basically, of buttressing and ground improvement, deep soil mixing, shear panels at the toe of those existing tailing dams. So here you can see the type of size we're talking about. So the tailing dams are roughly 10-12 meter high, and we came up with some shear panels of roughly 7 to 10 meters in width, and we went down to the more competent soil. In this case, it was very soft, silty clay over till or bedrock, and so we covered the whole section there. Many slope stability analyses were performed, of course, in order to better to work the best geometry as possible in order to build those panels. The first step while doing soil mixing is to make sure, basically, that that soil can be mixed and can meet your performance criteria. So you're building literally a natural concrete, so there will be variability in your results. So that's a very important thing to notice when you do your design, is that your design needs to be suited or to be done so you can accommodate some of that variability, and that's inherent to any soil mixing job, because you have different soil profile, different water content, and this will affect, of course, the end result of what you'll be mixing. So the first thing, very important, is to collect samples and to run some mix design bench scale test in laboratory to validate the soil mixability and also the cement dosage that's needed to meet your design criteria. After that, another good tool, I'd say, to help you with the preliminary design even before you do any work, you can. There are some good reference in the market. One of them is the Federal Highway Administration Design Manual on deep soil mixing. That guideline, the FHWA guideline, is fairly good to capture actually the risk of the variability in your soil mixing panels. So it gives you also some good references to validate for the extrusion, let's say, between the panels. So the creep that could occur between the panels, and also the panel integrity. So the structural integrity of your panel. So these are, of course, preliminary validation, but this is a very good step to include in your preliminary design for stability improvement using soil mixing panels or even columns. So in the case we're talking about here at that mine site, what we've performed is basically large shear panels at the toe of the embankment. Most of the panels consisted of 3 to 4 big columns. So here we were using 8-foot columns or 2.4 meter diameter column, secant, and we were building that type of geometry here that you can see at the toe. So we treated basically close to 2 kilometers of tailings dam using that type of geometry. The spacing between the panels were between 7 and 9 meters. When it comes to final design or very like fine tuning your design, you can also work with finite element modeling, right? Here we've conducted a few validation of the extrusion in between the panels and the physical integrity using Plaxis 3D. So this is even more important if you have a very weak type of clay, for example, where you suspect that there could be extrusion. So here's a few pictures of what it might look like. So you can see here at the bottom right some large size, large diameter augers. You have crane mounted type of equipment. Here we were working with a partner, GeoSolution. So crane mounted type of equipment or rig mounted type of equipment. It's the same type of auger on both of these equipment. So we basically drilled more than 400 DSM columns using 2 crews in less than 3 months. On that picture here, you can see those little pools. Each pool represents basically a shear panel consisting of 3 columns. So you can see that's the way. Of course, it's generating spoils. So spoil management is also something that you need to consider in your project. Here it was easy because these spoils were reused for the construction of the embankment. Here's a larger or more overview of the site. So you have a rig. Of course, you have a batch plant. Here the batch plant was there. It was our last panel here to do. Here we were going down to 18 meters roughly. Pumping distances can be up to, I'd say, 1 kilometer. That's a typical distance. Of course, as close as possible is always better. So the batch plant is there. You need to make sure that you have delivery routes for your cement trucks, and then you have a line. You pump through a line and down to the rig. Everything is instrumented, full-time monitoring of what's being installed, and that's it. So I think that concludes the soil mixing. So I'll give the mic to David. That's gonna treat about the seepage and the construction optimization now. Thank you.
Great. Thanks, Hubert. So yeah, Hubert touched upon solutions that we have for stability problems and failure modes. But one of the other failure modes that was in that pie chart at the beginning was more environmentally related, whether it's seepage of groundwater flow or contaminants beneath or through your tailings dam or facility. And I'll touch on a little bit of what we can do to solve for that problem. Let's see if I can move the slides myself here. Okay. So a cutoff wall is a very traditional way of installing an impermeable barrier. I'll talk about a couple different methods here. We have, of course, we offer a wide variety of different ways of installing cutoff walls, depending on the depth in the soil and your geography and geometry of your alignment. But these two kind of primary ways are pretty robust, simple solutions, and they're pretty effective. So to start with the soil bentonite walls, this is another type of mixing method almost, where you're mixing the soil in with bentonite slurry. So you start by hydrating bentonite on site to create a slurry. And as you excavate along the alignment, we use a specialized long reach excavator to excavate. You actually mix the spoils on surface. You mix the spoils with the bentonite slurry to create a soil bentonite construction material, so to speak. And then that material is replaced back into the wall, creating an impermeable barrier. You can reach really low permeability specs, 10 to the -8 or even less centimeters per second via this method. But of course, because you're using your soil as a construction material, oh, skipped ahead too far. Because you're using soil as a construction material, and like with many other ground improvement techniques, the type of soil you're using has to be part of the design process. So if you're using a very coarse soil, it may be difficult to reach those lower permeability specifications. And or if you're using really fine, stiff clay, getting the mixing energy to adequately mix that clay in with the bentonite may be problematic also. So depending on your situation, occasionally you may have to bring in additional material to mix with the bentonite, whether it's substituting a little bit of material or completely substituting brand new soil for the soil bentonite wall. The other type of wall we can construct here is cement bentonite. Oh, too far again, sorry. Cement bentonite walls. So this would be more for if you're looking for a compressive strength spec along with the permeability spec. We actually mobilize a batch plant site similar to soil mixing. We have a cement batching and we have a hydration tank for bentonite. We'll batch the two together and pump it out. Again, we can pump it about 1 kilometer, maybe a little bit less, maybe a little bit further. We can also add satellite pumping stations if we need to get a little bit extra distance in, and we're pouring the slurry directly at the working excavation phase. So as the excavator is excavating the wall, we're pouring the slurry directly in. It's self-hardening. So the slurry does two things. It creates trench support. It gives you that static head to help control the trench wall from collapsing. And then it also hardens as you go. So you would construct it in panels. You complete one panel, you come back the next day, it's already semi-cured, and then you start by tying immediately into that panel. Both of these solutions, as simple as they sound, they're really effective at guaranteeing that you get a continuous wall from both from surface down to your anchoring layer and horizontally across. So an example of a case study, I guess, of when we did this in Thompson, Manitoba. So it was, as you can see the profile here, a small tailings dam, and beneath the tailings dam was a pervious layer. It was slag and sand, and then about 6 meters beneath that, we had an impervious clay. So that slag layer is what we were most worried about. We started with compacting the slag layer. So in order to provide that extra trench support, compacting that layer was critical. We brought in this unit here. It's a rapid impact compaction. So it's similar to dynamic compaction, but it's when you don't need to go very deep, it's really efficient for doing a great surface area. Secondly, then we came in with the cutoff wall. So once the area was compacted, we came in and did a cement bentonite cutoff wall. As you can see here, the excavator is digging along, starting a new panel. This is the semi-cured panel from probably the night before. And you can see the slurry line, and that would be pumping slurry the entire time he's excavating. With the CB wall, as opposed to the SB wall, you do have to dispose of all your spoils, so you'll have trucks backing up and dispose of them. But there's also, of course, a combination of the two. You can do a cement bentonite soil, cement soil bentonite wall. As with many of our techniques, they work together very well. So I'll quickly get through this last little section here, but we've been talking about risk mitigation a lot, but we also have solutions for optimizing construction. One of them is a very Menard method. It's dynamic compaction. So this is dropping a big weight, a pounder from a crane, certain heights, and compacting the ground beneath it. Our typical dynamic compaction units are 300 ton meters around that. That's the weight of the pounder times the height of the drop. And this can compact in appropriate soils. It can compact about 10 to 12 meters of ground. If you need less, like I mentioned before, the rapid impact compaction is extremely efficient in that. And then there's also been cases where we've built larger machines if we need to go very deep. The way it works is the pounder drops, it creates two waves, a P wave and an S wave. It increases the pore water pressure, which takes the loose soil, creates flotation or localized liquefaction. The shear wave rearranges the particles and it settles into a denser formation, compacting the whole thing. And there's a bit of a workflow to it also, where we don't want to just compact from one side to the other in a grid. Otherwise, we're going to end up with a very compact surface and we won't be able to penetrate to those deeper treatment zones. So we start with a phase one, which is more spread out, and really adding many drops to compact that deep zone, followed by multiple other phases. I think in this we have 3 phases, but by the end, you're only compacting, as you can see, the very surface of the deposit. And again, this is applicable to certain soil type specifically. So we're looking a lot at like sand and gravels and those coarser materials. We're really targeting less than 35% silt and only a couple 2 to 3% clay tops. You really need that time for the pore pressure to dissipate before dropping the pounder again, and that's critical. And you can add instrumentation like vibration monitoring or piezometers to look at that pore pressure dissipation, so you can time out your blows appropriately. This is just a quick example of when we did it. This is a mine operator up in Nunavut, and they had to drain a portion of this lake to expand their open pit operations. So they were constructing a wall across the lake and draining the north end. They started with excavating some of the material on the seabed, the frost material, and filling in with 3/4 inch rock fill. Once they filled up above the water surface, traditional methods of compaction weren't viable anymore. They required about 10 meters of compaction at that point. So we came in with dynamic compaction unit, 15-ton weight, 18-meter drop height, and we were able to compact the entire dike as we went. And we actually did it in 2 stages. So by the end, we did 1 pass, a lift, and then the second pass, by the end, we were at a 3 to 14 meters of compaction in total. And here's just an example of how it went. So for the really shallow stuff near the ends, very, very simple, just a couple drops per phase. But when you're getting into those deeper treatment zones, 10 meters or so, you're really loading up the phase one with 40 drops and reducing it as you go. By the time you get to, we did 4 phases here. By the time you get to that last phase, it's really just an ironing phase to kind of sweep over the surface of the entire area. And I think we already have some questions, but yeah, feel free to leave some questions in the chat there or raise your hand maybe, and we can answer some questions.
Okay, well, yeah, thank you. So thank you, Dave. So yeah, as you can see, we it was really a summary. We went over the main topics, let's say. There are, of course, many more details to be discussed. That was really an introduction. So, of course, if you have questions, I mean, we'll be more than happy to answer them. If you have anything, you can send us an email as well. I'll go through a few questions now. We still have a few minutes left so I can go and look at the chat here. So we have question about the risk of liquefaction when, yeah, so that's it. When we're using any of these techniques, let's say dynamic compaction, or vibro compaction or stone columns even, when we're doing the ground improvement, we need to make sure that we're monitoring the site in order not to create a problem. Because you're right, sometimes we're liquefying a small portion of the zone. So we're generating poor water pressure. So that operation, it is very important that it's being monitored. And it should be monitored, real-time monitored as well. There are ways to try to mitigate that risk of instability, but of course we need to very be cautious. So I don't have a specific answer on. So it has to be adapted project to project, right? So you cannot just use dynamic compaction blindly at the toe of a berm to fix an issue. You need to make sure that you understand the global stability and also the effect that you might have on the structure. So for that, we need to go on a case-by-case basis. So for the depth, oh yeah, good question for the slurry walls and all that. So the maximum depth is using an excavator that we're doing right now is close to 27, 28 meters technically. So this will be the biggest reach. After that, you need to go with clamshell. So clamshell will be crane mounted, and that can go very deep. At one point, you know, the slurry wall depth. I mean, it's a matter also if you're going with let's say with panels, you have also challenges when it comes to alignment and continuity, because you can have deviation with depth. So as the deeper you go, the more deviation you can get if you're using clamshell, or even worse if you're using, let's say, a column. So that's a good point. Thank you for that question. I won't be, so if you, I see in the chat that there's many questions that are more like project related or specific project related. We'll send you we'll put our emails at the end of the presentation. If you have specific project questions, please send us an email with some geotechnical data or geometry data, and we'll be more than happy to look into it. But I won't be answering questions on specific projects in this chat here. Okay, so for the dynamic compaction, what depth can it reach? So in very good conditions, so well-graded material, easily compactable material, dynamic compaction can reach 10 to 12 meters in depth. If you need to go deeper than that, then we need to use the vibro. So the vibro densification using a vibrating probe. And I think we own the record here in Canada, in Quebec, actually. I think we've done 52 meters in terms of depth using the vibro densification method for Hydro-Quebec. So that was another question. I see there's tons of questions. That's great. Thank you for all that.
Soil mixing, if the water table is high, that's a really good question. Of course, water can impact the mix ratio of the soil. That's part of the soil mixing operation, is doing a detailed design, bench scale design with soil samples. So we absolutely need to collect soil samples, look at the moisture content, look at where the water table is, to help us design for that, so we can achieve the right water to cement ratio there.
Yeah, good point. So in terms of costs, okay, I see a few questions. Of course, I won't be specifically, again, we can have a look at your specific projects, but in terms of cost, the cheapest method would be the dynamic compaction. The mobilization cost, of course, depends on the distance to mobilize and the size of equipment to be mobilized. After that, you have vibro densification without the stone. Okay, so it's just a crane and a vibrator. After that, you'll go into the vibro replacement or stone column. There, the price is going to increase a bit. After that, you'll have let's say per volume, let's say you would fall into the soil bentonite type of slurry wall, then the cement bentonite, and then the soil mixing would be after. Soil mixing is a bit more expensive. It still is way cheaper than structural solutions like sheet piles or other secant piles, for example. We're using the soil itself and some cement slurry to do a natural concrete. So it's cheaper than just like pouring concrete. But it's a bit more expensive than the other techniques because we have to bring a batching plant. So when we need to batch plant and we need to use cement, well, of course, that brings a higher cost. It's also a bit more of mobilization cost because we have to assemble all of those elements: the batching plant, the rig, and the support equipments. Any other? So we use Plexus in our modeling most of the time. We do also have some in-house spreadsheet that we use that we've developed through the years. It's you know, a lot of ground improvement is semi-empirical, so we rely also on our experience and on the large number of projects that we've performed through the years. So that, of course, that helps us when it comes to designing a project. So it's not only modeling, really. It's hard to model. For example, that dynamic compaction is very difficult to model. Dynamic compaction, of course, is one of the most vibrating techniques. So it will cause some vibration. So what we usually do, so we have a vast database giving us the distances, the vibrations function of distance of the impact point. So we've monitored hundreds and hundreds of projects. So we have that database. So it helps us when looking at distances where it's suitable, where it can be suitable. And so yes, you need to be concerned. Vibro compaction, vibro densification as well. It generates a bit of vibration, not much. Soil mixing is vibration free, basically. But still, you need to make sure that you're not remolding too much of large of a zone. And you need to think about that with the curing time and sequence, not to, if you're going in a very sensitive zone, you need to make sure that you have a very safe working platform, and also that you're sequencing your work in order to make sure that you're not let's say lowering the safety factor unreasonably. Okay, I think there are many questions, so I'm jumping from one to the other. It's very interesting. So I think what we can do, Jennifer, maybe, or if we can give our emails, I think we'll
Yeah, we
close
will
it here
answer
now.
directly to each question. Yeah.
So we'll answer to the questions. And again, if you have specific questions, please send us an email with a minimum of data on your project so we can help you and figure it out. So there will be other seminars or webinars like this one given by our colleagues of different regions in Canada. The next one, I believe, is in June, and it will be more like for smaller residential buildings. Then there will be another webinar more on environmental sustainability and ground improvement. So how the ground improvement solutions are let's say, we're doing optimization, so we're reducing our footprint, the carbon footprint, and we're going to show you some example on how it can help you to reduce your carbon footprint and have a better environmental performance. And then we'll finish with the industrial building and warehouse webinar. We've been doing tons of warehouse across North America using ground improvement. So that last webinar will talk about that topic. So on that, well, thank you all for attending, and thank you for your many questions, and be sure that we'll connect with you to answer them.
Thank you.
Thank you. Thank you, Dave. Thank you, Jennifer.
Thank you.